In this video, we're going to explore the connection between the time series that we saw here and two alternative versions of the frequency domain results, where we plotted the magnitude of the Fourier series coefficients. And here we had the default presentation of 0 to n minus 1, or here it was 16, so 16 minus 1, 15, versus the symmetric representation of that same data, where we moved all of the elements here from 9 on, moved them over to the left-hand side, and then we could see the symmetry around 0 that otherwise might not have been obvious to us. What we're going to try to do now is ask, let's say for a particular instance, let's take number 14 here. Number 14 would have been mapped to number 2 over here. So the claim that I would make is that we should investigate is why is the 14th Fourier series coefficient equivalent to the negative second Fourier series coefficient. Now, what does minus 2 mean? That'll be a separate issue, but for now it's just enough to map between those two. Let's start with the one that we know how to define. So this is what we get out of the code in Python, and it naturally defines 0 to 15 coefficients. Again, we're just going to pick the 14th as an exemplar here. And remember that Fourier series coefficient comes from a sum up to 15 here, in general n minus 1. I'm going to try to keep it specific for the purposes of this. And then it required the real data, and then we had this funky exponential. In fact, we're going to need more room for that funky exponential because it is such a big exponent. E to the negative 2 pi I. And again, remembering this is like a dot product we were doing. The 2 pi multiplier, actually we did that over 16. That gave us the right period. And then we multiplied by n. That's the same n as our series, so that's our dot product. Take the first times the first, second times the second, and so on. And then the second thing that we had up there as well was the 14. And just remembering our general pattern, this was f hat of k, sometimes also called ck. And so this was a k for the 14. What we're going to try to do is see if we can get to the same place as f negative 2 hat, which, if we just use the same symbols, is all of this. The only thing that we're changing, negative 2 pi I over 16, n times, well, negative 2 here. Let's highlight that contrast over here as well, just to make it obvious that that's the feature of interest and that it ties back to the numbers down here. The key observation that's going to help us see that these are actually equal to one another is the observation that e to the it has a 2 pi periodic cycle. Remembering that if we put an angle in here for t, then that reflects the point on the complex plane in a circle. Now when we do negative 2 pi over 16, that's going to be going the other direction by fractions of 1/16 of a cycle. So 1/16, 2/16, and so on. So we're going to just rewrite this a smidge. Sum up to 15, n equals 0. And again, this is just counting off the real data points, 1, 2, 0, 1, 2, 3 to 15. And then we multiply that by negative 2 pi i's. And here's what we're going to do. We're going to take the n, and we're going to put negative 2 over 16. I'm going to leave the bracket open there a bit. The idea being, this is all multiplied. And if I end up multiplying by another multiple of 2 pi I, that'll take me one full cycle around. If I just add 1 to this, then I'm getting another multiple of 2 pi. Maybe an n, but n is also an integer, so it'll be maybe 4 pi or 6 pi. Just more and more and more full cycles being the key ingredient here. So if I add 1 to here, I'm getting to the same place as if I didn't have the plus 1. So that's optional. Well, I don't have to call number 1 number 1. I could call it 16 over 16. And hopefully you see what we get when we add those together. We get 14 over 16. Well, that, by the time we put the 14 and the 16 together here, shows that those are identical. Anytime we have an index of 14, we can add any number of 16 multipliers. So that's actually the same if we wanted to, of 14 plus 16 is 30, or we could do another f hat of 46, or going the other direction, this is where we subtract 16 and we get -2, and we could keep going down the other direction. Now this may feel completely bizarre, and it kind of should, because these are actually frequencies in hertz. We're saying they're the same. What does that mean? It's less surprising when we go back to the roots here. If you remember how we construct this time series, and then we built it out of sine and cosines, what we were implicitly assuming there is that we had a periodic function in the time series as well. And so it shouldn't come as a huge shock. So it was the same value. By using sines and cosines, which repeat every 16 cycles here, every 16 indices, it shouldn't be totally surprising that when we transform it, we also get 16 periodic coefficients for our Taylor series. Now, in practice, do we care about any of these guys? No, we don't, but it's enough to show that the -2 and the 14 are the same. So it is completely legitimate to take the natural or the default presentation of the Fourier transform, counting from 0 as a vector up to 15, that's all great, and simply take those last, that's last 7, so n/2 minus 1, and sorry, that's big N/2. Take the last 7 and move them onto the other side of 0 to get this kind of plot. In some sense, this is a better representation of what we actually have. We have information on frequencies in this range. We don't actually have that information that we might think we have in this upper end here, because it's just a copy of what we saw earlier. All right, now next up is the second question that we had, which is, why is the coefficient that we get for 2 almost equal to the coefficient that we got with -2, except we're going to put this bar here, and just remembering that z bar is something that we get if we take a complex number, and all it means is that we subtract, or change the sign of, technically, we're going to flip the sign of the imaginary part, and this is the complex conjugate. That's one way to imagine it. The other way to think about it is, if we think about it in exponential terms, if we have a line like this with an angle of t and a radius of 1, because we're dealing with all these exponentials that are the same radius ones, and if we do the -t, that also gives us the complex conjugate. So if I take e to the it and do the complex conjugate of it, preferably without going through the other letters, then that's exactly the same as e to the -it. All we have to do is swap the sign in the exponent, because that changes the angle to count in the other direction. So complex conjugates have really nice, simple relationships when we look at them, both in the Cartesian, a plus bi, the left and left, right, up and down, and also the angular forms. Well, let's just compare these two values here. If we take a look at our second coefficient for the Fourier series, it's the sum from n equals 0 to 15. Let's keep it concrete here. For our series, the original data series, so f0, f1, f2, the original time points and their associated values, e to the -2 pi I all over 16 times n times 2. So that's our k. And again, I'll highlight the relationship here by using the same color. While its partner one, f-2 with a hat, and again, do that in color, this time we'll use red, that is equal to the sum to 15 if n equals 0, our data points in time, e to the -2 pi I over 16 times n. Again, the n is just the dot product. We go n equals 0, n equals 1, n equals 2, and so on. And this time it's times -2. And hopefully you can see the relationship right away. All we did is swap 2 for -2. So when we expand this out, this would become positive, or they have opposite signs in the exponent. And the consequence of that is that each of these individual terms is a complex conjugate, and it shouldn't come as a shock if we add up a bunch of things where we flip the sign or flip the angle, flip the sign of the imaginary part or flip the angle, we also get a complex conjugate. And so we get that f2 hat is the same as f negative 2 hat, except you can put the complex conjugate on either side, actually. But let's put it here. Now, a consequence of that is if we just flip the sign of the imaginary part or we just flip the angle, the magnitude doesn't change. So if you talk about the magnitude of that second coefficient, it's going to equal, with a hat, the magnitude of the negative 2 coefficient, because they're essentially the same vector just in a different location, but their magnitude is going to be the same. And that's exactly what we see here. When we turned all these coefficients in their negative order, we saw f with a negative k, those coefficients, when we did the absolute value in Python, we got the same thing when we did the positive k's, again, hats to indicate that we're in the frequency domain. The fact that these opposite values on this chart had exactly the same magnitudes was not a coincidence. It was a direct result of the Fourier series structure. So if we have real numbers, we ended up with the cyclic behavior for the coefficients. If it helps us at all, we can add or subtract the number of data points from our indices here, and we can do that. And when we do that and we see things that are symmetric across the zero line, across the zero frequency line, then we know if we jump across the line, we get the same number back, the same coefficient, only complex conjugate. So, quick summary of that. If we have n data points, we're going to get that the frequency domain coefficient can be replaced by the same coefficient at plus n, or the same frequency, and this one we used was at minus n. And when we do that, we also find the relationship that if we have a positive k and we replace it with the negative version of that, when we do that, we just need to take the complex conjugate. And this is our redundancy effect that we talked about in an earlier discussion. We have 16 values here, but they're all complex, so it's 32 actual numbers. But by the time we recognize this structure here, not all the numbers are independent anymore. This would be, if I knew all of these numbers, I'd know 16 numbers here, and then this would be the other 16 are defined immediately because they have to be the complex conjugate of the first 16. Now, what does that mean for us in terms of interpretation? I'm just going to erase this because it's not always 16, and I don't want to get that in our general statement. But what it means for us here is that past 8, which is n over 2, so n over 2 here, everything beyond there could be moved to the other side, absolutely. But even if we do that, we know exactly what it's going to be because it's the complex conjugate of the first 8, 7 technically, 1 through 8 here values. And so these coefficients past the halfway mark are actually containing no information. They can't be interpreted in the same way as we interpret the first half of the data points here. Let's capture that as the fact that there's only, I'm going to say useful, but another way to phrase it would be unique information in the first half. First or lower half of the coefficients as a function of frequency. This interval here doesn't mean what we think it means. It's just a carbon copy of what came earlier. And you might hear references to something called the Nyquist criterion. That's actually a little richer than what we're talking about here, but it has the same flavor. And it basically says that we need to sample at twice the frequency, twice the max frequency. We want to analyze, or we want to capture. If you think of this as the audio clips that we've seen, the frequency domain went up the sampling rate, so 22,000 hertz, but we can actually only use the values up to 11,000 hertz. So we sample at 22,000, but there's only real information about the first 11,000, or half of that. So that plays a role in how we design our sampling strategies. And one last property we haven't talked about is just going back to the original data set here. If you take a careful look at the values, they're all centered around 1. And if you take a look at the 0th coefficient, which notice is unchanged as we went through all this silliness, it was the one that didn't move at all, its value was pretty close to 16. Well, if you think about that 0 value, it's the sum of all the function values from n equals 0 to big N minus 1 here, in the general case, and times e to the, times e to the 0. Well, e to the 0 is just 1, and so this is just the sum of all the measurements. So if you're looking for some explanation for why this first coefficient, or the 0th coefficient, spikes when you have a big data set, it's because you have a lot of data. Literally, it's just adding up the number of data values. And that's why frequently we don't use the 0 value as a scaling value, because it has a very different flavor than the other values. It's also worth noting that it's therefore going to be a real number just by default. All the other values, aside from the one at 8, we'll talk about that some other time, the vast majority of the other values are complex numbers. They have rotation and they have lengths. That 0th value is going to be all real because all it is the total of all the values in your data set. And that should do for now. That's quite a tour of the math and the exponential structure of our Fourier series and the consequences, specifically when we're dealing with data coming off of a machine typically, which is a real signal measured over time.